Okay, so let's move on to problem 6, and it's about this an equation involving this quadratic form, which defines a quadric surface in 3 dimensions. And the first thing we're asked is to express it in this matrix form, where A is a symmetric square matrix and V is the vector of coordinates. And we're told that the eigenvalues are -3, -3, -7, -1. And we're asked to write down the equation of the surface in terms of variables big X, Y, and Z, which are relative to the principal axes. And then we're asked to identify the type of surface and sketch it relative to its principal axis. So here's how we go about solving that. So the first thing we've got to do is to establish the quadric form. And the list of variables, which will be X, Y, and Z. And now the way we calculate this matrix is to compute all 9 mixed partial derivatives, second-order partial derivatives with respect to X, Y, and Z. And we can do that using that, and we have to remember to divide by 2 to avoid counting things twice. And we can visualize that in matrix form using this, and then we can enter the eigenvalues using this, hoping that they're correct, and we can establish this quadric form in the principal axis coordinate system using that. It's much simpler, and we can see that we could easily solve this, most easily solve this for X as a function of Y and Z using that. And then you can see there are 2 solutions, and we can plot those solutions using this. And we can see that this is a hyperboloid of 1 sheet with a hole in the middle. We can sort of move it around and look something like that, and then we can sort of goes like that. So that's what it is, and that fits in with the rules that if if 2 of these are negative, then it's a hyperboloid of 1 sheet. Now we go on to question 7, the last one, and this is we're asked to look at this matrix A, and we're asked to find its eigenvalues and eigenvectors, and then we're asked to use that to solve this system of differential equations. And if we look at the top row of the matrix, we can see that that's equal to the coefficient of X and Y in the first equation, and likewise in the second. So let's go and do that. So we establish the matrix using this, and visualize it in matrix form like that, so it looks okay to me. And then we can obtain its eigenvalues by taking the matrix, subtracting off lambda times the 2 by 2 identity matrix, and taking the determinant. And that will give us an equation for lambda, which looks like that, and we can solve that using that to find that the eigenvalues are 5 and 6. Well, now we go on to calculate the eigenvectors, for the first one. So we take the matrix whose determinant we found, and we evaluate that at the first argument value to give that. And we can see that the first row is -2 times the second row, so that means that it is an argument. The matrix will be singular, so that's correct. And the eigenvalue, if we choose the second element of the eigenvector to be 1, then the first element is -1. So that's the first eigenvector, but just to be sure, let us check it using this. And indeed, we get 0. So the second eigenvector is very similar. We now evaluate that matrix at the second eigenvalue, and we can see that the second row is the negative of the first row, so that tells us that the eigenvector must be, if we let the second element be 1, then the first element is -2, and there we go. But as I said, as we did before, we'll just check that we've found an eigenvector. And we have. So now we have to solve the differential equations. So let's define the vectors or the variables using that. And we can establish the differential equations using that. And that's what we started with. And finally, we can calculate the solution, or the general solution, by taking a constant a, multiplying it by the exponential of the first eigenvalue times t, and that by the first eigenvector, and likewise another coefficient, the exponential of the second eigenvalue times t, and then multiply it by the second eigenvector. So we do all that, and there's a solution. So that's the solution to those problems.